Hi, and welcome to this podcast with the title Multistep Synthesis followed by a Benchtop NMR, a substituted para-terphenyl derivative utilizing the Diels-Alder reaction. My name is Alex, and I'm an application chemist at Nanalysis. In this talk, I would like to start with an introduction on integration of NMR technology in teaching. After that, I'm going to present a three-step synthesis procedure highly suitable for organic chemistry laboratory courses, where we will discuss the experimental procedure as well as the characterization of each step via benchtop proton NMR spectroscopy. After a closer look on the Diels-Alder reaction, I will close with a discussion on second-order effects and how to practically choose experiments for low-field NMR spectroscopy and academic teaching. Knowledge cannot be passed verbally. Students should be active participants in the learning process, so they might construct knowledge with their own minds. This quote might be more relevant than ever. While we need to adapt to the pandemic situation and find suitable ways for teaching, we cannot ignore that meaningful learning is said to require three things: cognitive, actual understanding of the material; affective, the feeling associated with this material; and psychomotor learning. This is particularly important in a physical science like chemistry. In laboratory courses, students can interact with colleagues and teachers directly. Instructions can be given on a more personalized level in accordance with the individual promotion requirements. Guided inquiry and discovery sensations allow students to learn the best possible way. Therefore, it is common to include characterization techniques within the laboratory course. However, if you view how often techniques are reported in the literature and how often students use them in the lab, there's a bit of a mismatch. By far the most reported analytical method in organic and inorganic chemistry publications is NMR spectroscopy. Also, in the Journal of Solid-State Chemistry and the Journal of Physical Chemistry A and B, NMR spectroscopy is one of the most significant reported methods. In contrast to its dominating application in academic research analysis, NMR technology in teaching is often still limited. This can be addressed by the fact that high-field NMR spectrometers are not easily affordable or accessible due to high capital costs and operating expenditures. Specially trained staff is required to maintain the liquid cryogen-consuming instruments. The spectrometers at universities are often working to capacity, whereas not often teaching is considered with a lot of hands-on time, and further the accessibility is limited as the NMR facility might not even be in the same building as the lab course. Because of this, NMR spectroscopy is often introduced on the dry and theoretical level, where handouts are used for explaining the practical steps for NMR data acquisition instead of hands-on learning. The actual spectra come from either databases or previous recorded data from the TA. In the nicest scenario, students can give their own samples to the analytical department and wait for receiving their spectra, but still missing the actual hands-on experience. By equipping the teaching lab with a benchtop NMR, the students can acquire their spectra themselves, learning how to set up an experiment easily and receive the NMR spectrum directly. In this case, the students can even learn how NMR-specific parameters can be adjusted and what effect each of them has on the resulting spectrum. Such benchtop NMR devices have been around since the 2010s and result from the miniaturization of NMR technology. On the left, you can see a regular so-called high-field NMR spectrometer consisting of three components: the cryogen-cooled superconducting magnet, the so-called console containing all the electronics for the communication between the probe inside the magnet, and the computer, which makes the final component of the setup. For our benchtop NMR, all these components are combined in a single all-in-one enclosure: electronics, computer, and magnet. The electronics are mounted on a single circuit board. An internal computer is available, but you also can use an external computer for controlling the spectrometer and processing the NMR data if you like. The magnet is a 1.4 Tesla hybrid Halbach neodymium iron-boron magnet, which corresponds to 60 MHz in the proton channel. As the system is based on permanent magnet technology, no cryogens are required, and there are even no moving parts which might get stuck and cause interruption of measurement operation. Automatable features like automated shimming allows the user to fully focus on the experiment. So how can benchtop NMR be classified and what can you expect from it? In our eyes, low-field, high-resolution benchtop NMR spectrometers add another layer of NMR technology to fill the gap between relaxometers and high-field NMR spectrometers. While the resolution and sensitivity increase towards high-field instruments, so do cost and expertise level necessary for working with these instruments. On the other side, robustness and accessibility increase towards relaxometers. Our vision of benchtop NMR spectroscopy is not to replace high-field NMR by any means, but rather bring this powerful analytical technique to applications and places where it hasn't been employed so far. It is affordable, accessible, and still features high resolution and sensitivity. This makes it the ideal instrument not only for industrial applications or reaction monitoring, but also for structure elucidation and academic teaching. Students can run their own samples right next to the fume hood they've been working in on an easy-to-use spectrometer, making NMR a fun technique to use. Understanding NMR spectroscopy is a very important topic in chemical education. However, there is little agreement on when or how to introduce this powerful characterization technique to undergraduates. Some introduce this as soon as first year, some in second. One of the most common strategies is to introduce NMR spectroscopy in the lecture component of introductory organic chemistry. Some focus on the simplicity of symmetry and carbon NMR, whereas many start off with proton NMR. For proton NMR, the key concepts require students to focus on three pieces of information simultaneously. A. The chemical shift, representing the chemical environment of a nucleus. B. The peak integration, which corresponds to the number of nuclei in the analyte signal. And C. The multiplicity, reflecting the intramolecular connectivity of the compound. By introducing carbon NMR first, students can focus on understanding the chemical shift before dealing with integration and multiplicity in proton NMR. For example, the hydrochlorination of carbone can be used as a carbon NMR sample experiment. Here, only one of the four possible chlorinated products is formed. This can be unambiguously confirmed by simply counting the number of primary, secondary, tertiary, and quaternary carbon atoms, as observed in this respective depth and 1D carbon spectra. Now I would like to present a proton NMR sample experiment to you, which can directly be adopted for your organic undergrad lab course. The procedure is based on an article from the Journal of Chemical Education and features a three-step synthesis of a para-terphenyl derivative, including the renowned Diels-Alder reaction. Remarkably, the experiments can be performed within 2 to 3 quick lab sessions, including the acquisition of a 1D proton NMR spectrum for each step. We start with the Diels-Alder reaction of diene 1 and the acetylene dienophile in mesitylene at reflux for half an hour to generate the dihydroterphenyl species 2 in 67% yield. Isomerization of 1,4-dihydrocyclohexadiene derivative 2 under basic conditions in methanol leads to the 2,3-dihydroderivative 3 in excellent yield. The dehydrogenation reaction employing DBU and bromotrichloromethane in DCM yields the para-terphenyl 4 in 88%, which corresponds to 54% yield over 3 steps. Each of the products was obtained as a white solid and can successfully be characterized by proton benchtop NMR spectroscopy. Interestingly, the stereoselectivity of the Diels-Alder reaction can be rationalized by frontier molecular orbital theory and confirmed with the acquired spectra by the students. I would like to present the 60 MHz proton NMR spectrum of the Diels-Alder product 2 from the first step of the synthesis. As you can see in the aromatic region, the signal of the phenyl groups is observed as a singlet at 7.29 ppm. The olefinic hydrogen atoms are observed at 5.77 ppm as a doublet with a J coupling constant of 1.8 Hz. The same coupling constant can be found for the doublet at 4.46 ppm, which identifies the benzylic proton in vicinal position to the alkene ones. The methyl group signal at 3.55 ppm is clearly recognized by the integration area of 6 and the multiplicity of a singlet due to the absence of neighboring protons. It should be noted that not only we can assign all the hydrogen atoms for this first intermediate product in the synthesis, but also we can confirm that there is only one set of signals present, which means that the Diels-Alder reaction is stereospecific, as we all know from the textbooks. Due to the symmetry of the molecule, the number of theoretically possible different stereoisomers reduces from 4 to 2. The enantiomers can be aligned by rotation and thereby are identical. If there were 2 diastereomers present, we would observe 2 signal sets in different intensities in the spectrum, as diastereomers can be differentiated by NMR spectroscopy. This observation perfectly agrees with the frontier molecular orbital theory, which we will look at in a few slides. The successful generation of isomerization product 3 can be confirmed by proton NMR as well. The aromatic hydrogen atoms appear as a multiplet in the range of 7.46 to 7.25 ppm due to the conjugated double bonds. The alkene signal shifted downfield to 6.56 ppm in comparison to the previous spectrum. Both the alkene and the vinyl protons are observed as singlets, not as doublets anymore. This is due to the absence of neighboring atoms. The methyl groups remain quite unchanged at 3.58 ppm. The final product, p-Terphenyl derivative 4, shows a very clear NMR spectrum with two singlets in the aromatic region at 7.48 and 7.37 ppm, and a singlet in the alkyl region at 3.58 ppm, which again can be assigned to the methyl groups in the molecule. After having confirmed the outcome of every single step of the presented synthesis, I would now like to take a brief look at the Diels-Alder reaction. The Diels-Alder reaction is not only the key step in this herein presented synthesis, but also it's just an awesome transformation. Otto Diels and Kurt Alder received the Nobel Prize in 1950 for the discovery and development of the diene synthesis. Today, every chemistry student knows the Diels-Alder reaction. It is formally a 4+2 cycloaddition, which is a subcategory of the pericyclic reactions. Pericyclic reactions proceed concerted. Besides the cycloadditions, there are electrocyclizations, sigmatropic reactions, and others like the ene reaction. In the Diels-Alder reaction, 3 pi bonds with 4 electrons coming from the diene and 2 electrons coming from the dienophile convert to 1 new pi bond and 2 sigma bonds, generating a 6-membered ring. Let's have a look at the energetic situation in the frontier molecular orbital diagram of this reaction. On the left, you can see the diene with the 4 different energy states ranging from 0 to 3 nodes. On the right, the 2 energy states of the dienophile are depicted. The diene counts 4 electrons, the dienophile counts 2, and we can assign the HOMO and LUMO accordingly. Because of the phenyl substituents on the diene and the electron withdrawing methyl ester functions on the dienophile, we are dealing with a normal electron demand Diels-Alder reaction. The HOMO of the electron-rich diene interacts with the LUMO of the electron-deficient dienophile, as this energy gap is smaller than the one between the LUMO of the diene and the HOMO of the dienophile. For inverse electron demand systems, this is just the other way around. Because of the orbital coefficients of the diene and the dienophile, the interaction proceeds suprafacial, which is allowed by the Woodward-Hoffmann rules. A multi-step synthesis including the well-known Diels-Alder reaction was performed, and every intermediate product was analyzed and confirmed by 60 MHz Benchtop NMR spectroscopy. This sample experiment can be utilized for a practical introduction of pericyclic reactions. Each step of the presented synthesis features short reaction times and good yields, making it a suitable experiment even for short lab sessions in the organic curriculum. The assignment of the proton NMR spectra is easy and in well agreement with the stereoselectivity of the Diels-Alder reaction. Chemical shift, integration, and multiplicity can be discussed in regard to the molecular structure of the synthesized compounds. We learned that size, cost, and the maintenance characteristics make Benchtop NMR instruments an attractive option for providing first or second year chemistry students with a hands-on introduction on NMR spectroscopy with high respect to meaningful learning. However, it should be noted that low-field instruments by nature are more prone to produce NMR spectra with second-order effects. In contrast to first-order, spectra with second-order effects cannot easily be interpreted by eye, and some information is not extractable. While there are plenty of compounds which do not show second-order effects at low field, just like the spectra we discussed in this presentation, there are others that do. This can be concerning for educators who do not want to add this extra layer of complexity to any analysis. To help address this concern, we recently submitted a paper to help educators overcoming this limitation. In this paper, we present a list of more than 200 molecules from 20 compound classes whose NMR spectra can be visually expected and interpreted using 60 MHz instruments. As an example, I would like to present a comparison of a series of alcohols at 60 MHz on the left and 400 MHz on the right. The stacked spectra of methanol, ethanol, propanol, butanol, and pentanol illustrate the differences between first and second order spectra. While the molecules only differ by additional methylene fragments, the coupling between all of these groups and small chemical shift differences lead to significant overlap in the region between 0 and 2 ppm. There are many more sample experiments accessible on our website. Please feel free to utilize these as a resource for your undergrad lab course. These cover a variety of chemistry departments. Inside you will find the theoretical background, results and discussion, the experimental procedure including pictures, and of course NMR spectra acquired on our Benchtop NMR instruments. I hope that you found this presentation helpful, and I would like to encourage you reaching out to us for any questions or discussion. Please visit our website or contact us directly. We would also appreciate if you would check our NMR blog from the resources section on our website and our social media profiles. Thank you and have a great day.